here we are with paper 6.3 from summer 21, and we're looking at cooling rates of different volumes of hot water. This is a question that it would be a good idea to think about your the main part of the syllabus. We do learn this in section 3, thermal physics. So if you're sort of thinking about cooling rates, etc., you're thinking about evaporation, you're thinking about drafts and volumes of water and area and lots of different things. Okay, so that could come up at some point, but for now we'll do a bit of reading. Okay, we're told a method here, which hopefully you've read. You're told that we are going to pour the hot water into the beaker. We're going to stir it, record the temperature, and every 30 seconds for 180 seconds. Okay, so we've got a table, quite a lot of filling in to do in this table. And you notice here I've actually remembered to start ticking things off. First thing, complete the column headings. Okay, add the units for time and temperature. Well, we're adding time in seconds because we were told we're measuring every 30 seconds. The temperature of both beakers X and Y in degrees Celsius. Okay. We're then going to complete the time column. Okay, nice and simple. We're going to go in steps of 30s. Okay, so 30, 60, 90, etc. Okay, and then we're asking us why we're waiting 30 seconds. Now, if we do this, I think we're worthwhile sort of looking at the question. You've got a thermometer. Now, as you know, a liquid and glass thermometer will take some time to respond to the temperature that it's measuring. So if you place a thermometer in the hot water, we'll have to wait for the temperature to the vertical column to rise to the correct height, and therefore use that to measure the temperature. So what's really happening there is we're looking at that you need to wait some time in order to allow the temperature the thermometer to adjust to measure the temperature of the hot water. Okay, that's what they've written here. Okay, to let the reading on the thermometer stabilize. That's a nice way of putting that. It means basically reaching a nice constant value, a nice value which is consistent with the temperature of the water and not the temperature of the surroundings, for example. We're then asked why we mix it. Okay, well, we want to mix the water so that we can make sure that the water is all at the same temperature. If you don't mix it, you may have a bit that's hot and a bit that's cold, and then measuring the temperature of the water would be difficult. Okay, that's much easier to do so if we're going to it's going to stir the water as well. Okay, I think we're going to start filling up our table now. There we go. All right, we are going to do our measurements here for beaker X and beaker Y, and these are the thermometer readings after 30 seconds. So we're going to record them in the table. Now, if we just look carefully again, it's one of these situations where CIE allows us to make readings which are perhaps slightly controversial. You'll notice on beaker X that the value is somewhere between 81, 2, 3 and 4. So we're going to call that 83.5. Again, I've said before, in my day you probably wouldn't get away with that, okay, but you are allowed to do that now. 83.5 is completely acceptable. And for beaker Y, we've got 81, 2, 3, 4 there. So we're going to put those values back into our table. Okay. You are allowed, if you want to know whether you're allowed to do that half division reading, look at the other data points. You'll notice there's some halves in both columns, and therefore that's going to be consistent with what CIE is allowing you to do. Okay, we're asked to calculate the decrease in the temperature, so I've just taken those values from the beginning to the end over the 180 seconds, and done both for our beakers X and Y. Okay, I should say one small point about the mark scheme, when we're measuring those temperatures, it's really important that you don't just write 84. We must write 84.0 because that shows us the precision of the equipment we're using. Okay, so just like when we're measuring lengths, make sure you're measuring to the nearest division, not ignoring that 0.0 just because you think it might not be important. It's very important. We're then asking to calculate the rate of cooling. We're told that we just find the decrease in temperature, divide by the time. And so we get 0.053. And we do the same for beaker Y using the same equation, just up at the top there. And we notice we have two different values. Now, we're then asked we're then told, sorry, the temperature of the water decreases, and we're asked one similarity. Well, if you notice, okay, that actually the rate of change of temperature decreases over time. If we have a little look here, just scroll down, it's a big question, this one. At the beginning, we have big changes, okay, so 86 to 83.5 to 81.5, but at the end, we've got much smaller changes. And what that means is the rate of cooling is changing. And we actually know this from our P3, okay, which is that actually as temperature goes down, the rate of cooling, the temperature goes down, the rate of cooling is also going to go down with it. And you can see that from the data. The teacher then says that the rating of cooling in the smaller volume of water should be greater than that of the larger volume. Okay, so let's have a look there. Okay, that we're going to say yes. Why? Well, if we notice there that if we look at beaker Y, okay, and we compare that to beaker X, in the same time frame, okay, beaker Y has got a change in temperature of 14.5 and beaker X has a change in temperature of 9.5. Okay, and so therefore they've got a bigger change in temperature. Beaker Y has a bigger change of temperature. All right, and so therefore it is going to have a greater rate of cooling. Why is that linked? Well, it's because we've looked at the same time frame. Yeah, and that's actually underlined in the mark scheme. So just be careful here. I think this is a mark that a lot of students wouldn't get. I don't even think I'd get this one. Is the idea that they have got a bigger temperature change in the same time frame. Okay, so we're thinking here about one of our control variables in this experiment, which is the time. All right, so we've got a reference to the results. Okay, the change in temperature is much greater for Y over the same period. And you notice I've calculated a percentage difference here. Thought that was a nice thing to do as well. Okay, last one. Another, we want to repeat the investigation to check the results. Okay, good. They're repeating things. That's good practice. State of variable should be kept the same. Well, we should use the same volumes, all right, the same amounts of water, okay, but also the same starting temperatures, really. It should, to be fair, okay. The temperature of the surroundings should be the same. Okay, there's lots of things. We notice here they've gone a bit over the top. Same size, material, thickness of beaker, same person, same location, same earth. Okay, I'm going a bit over the top there, but really the idea is that the experiment has to be the same. You need to be thinking about your control variables, and that's basically everything. If you want to confirm data, we really need to be careful with the setup of our experiment, and then go from there. All right, if you've got any questions, please let me know. I'm, as ever, happy to answer any. Thanks for watching.